graduate studies. My professor was a friend of my father from youth, got me a job moving numbers from Fluent to Excel, and I quite excelled at it. Now, after that, got hooked in CFD and decided it was my undergraduate studies, and decided I'm going to work in, that's what I'm going to do. My thesis was also CFD related, transition actually. After that, I worked in Israeli aerospace industries for about 4 years. Over there, it was more FSI than pure CFD. Trying to fix the camera so you'll see me fine. Okay. I've been there for 4 years. Then I've transferred to Elevate. In Elevate, I was the team leader of the analysis team. And when we're talking about Elevate, this means mostly thermal analysis of electronic equipment. I've been working there for 7 years. So you might call, I was so hooked on CFD, so that I would, in my thesis, I would walk and think about pseudospectra and bypass transition, and but you might say that my bread and butter was Elevate was thermal analysis of electronic equipment. And since we are kind of a startup nation, then you would say that many of the CFD and thermal investigations are related to electronic equipment, many of them to the defense industries. So that's what I did for 7 years. After that, most of you know me from Tenza, the X ANSYS channel partner. I've been there for 2 years. The blog all about CFD exists for about 7 years. Started it for fun, and I still do. There's no monetization in the blog. I didn't earn a single dime from the blog. Possibly a little bit of reputation, but it's mostly about my passion about CFD and physics in general. I'm kind of an eclectic person. I like to, I wake up every day at 4 o'clock, do some 2 hours of meditation, then a little bit of sports. Now I'm, as I left Tenzo, went on my own route. I have more of control of my time, so kind of an eclectic person, like to do a lot of stuff during the day. And CFD and physics are one of my big attractions, besides the spiritual part, which we'll not mention. We're not trying to convert you to Buddhist. So let's delve right into the world of thermal management and analysis of electronic equipment. There are links here. A link like that would probably lead you to the blog. Yeah, it will lead you to the blog. That's usually how I do my presentations, linked to references. And I want to say that I want this webinar to be interactive. I don't know how. I know there are many of you. I don't know how many, but it's about. It's about 30 participants at least, and it's going to be a lot more than that, as far as I know. You don't have to unmute yourself. You don't have to show your faces if you don't want to. You don't have to unmute yourself. You can ask a question whenever you want, whenever you don't understand something. If I don't know, if I swallow a word or it's a technical term that you don't understand, you can ask. I promise that for every single topic that will go on this presentation, might it be even a word like turbulence? If someone wants a reference, I mean, even the best reference in the world, he can contact me after the webinar, and I promise that I'll have this reference ready for him. So care to join me? So we start our voyage with some people that most of you know. Most of them are actually more known for other things they did. Someone wants to say, who are these people? I don't have comments because you would have seen them too. So, is there anyone out there?
Well, Newton, obviously.
Newton, obviously. That's Ludwig Boltzmann.
Yeah, Boltzmann.
Is it Fourier?
That's Fourier. Okay.
What's he called? Something like that.
Yeah, he did with Boltzmann the law of radiation. But all of them are known for much. Newton is known for all of our mathematics today, our physics language, and his laws of motion. Boltzmann is known for statistical mechanics and the concept of entropy. Fourier is a mathematician which is known for a lot of things. The first step you get for that, these are the modes of heat transfer. You might say that there's more modes of heat transfer, like phase change or but these are the main. That's when I call it modes of heat transfer. I mean conduction, convection, radiation. We all know the difference between them microscopically, but we are here not talking about microscopically. We are talking about an emergence theories. Everything you see here is emergent. I mean, there is a scale separation between the microscopic world and the equations we see right here. I might ask someone, what's the convection coefficient that you would take for a wall in natural convection, vertical wall? Someone has a suggestion?
10, I think.
On the wall itself, what would be the convection coefficient?
Natural convection?
Yeah, on the wall itself, yeah, on the vertical wall itself.
It will be natural convection.
I mean, it's a non-question. It's a question. There is no convection coefficient on the wall itself. the connection velocity, the velocity in a non-slip condition is 0. So it's a non-question. Your internet connection is unstable. That's something I didn't expect. I hope it will stay stable. So we're talking here on an emergent level. We're talking here about temperature. We're not talking about a microscopic level. There is no temperature of an atom. There is no temperature of a molecule. Temperature is an emergent quantity. So we're going to treat it like that. And for all purposes, there are conduction, convection, and radiation. The only one who doesn't work when molecules touch molecules is, of course, radiation. And the first step is to conduct load comparison. Actually do that in Excel. You can do that very easily. Write the equations in Excel and see how much radiation, especially for cases of natural convection, because this depends on the temperature difference. When the temperature difference is very high, like in space applications, then of course radiation has a big impact. You can see the fourth order in the equation. Just do a little. You can write the equations in Excel and then iteratively put numbers inside and see if you can neglect radiation, because afterwards you're going to conduct a CFD, and solving for radiation is like solving the CFD and another problem of radiation. There's two separate problems. We wouldn't like to do that if there's no need. So we need to decide if radiation is negligible or not. Perhaps we can get a bound, even if it's not negligible. We should think about that. Just the first page. So we're going to treat like we treat almost everywhere where we have component level chips that we might buy, or if like Intel maybe prepare, or maybe we need an ASICs of our own. We're going to treat it in a top-down manner, component level, board level, and then system level. This means we're going to start from component level, all the knowledge we need to know to control. When you open the slides, I hope you can, I think you can. The analysis guide will take you to whatever you need to know about it. And when we're talking about component level, what you see here is a chip, it's a Stratix, it's an FPGA, is a Stratix 5 dissipating 20 watts. FPGA is static heat dissipation is very high today. A chip which is 3 or 3.5 centimeters and 3.5 centimeters can dissipate even 30 watts. This means it needs an heatsink. In our case here, because of military standards, there's no way you can cool a component directly. So use ruggedized covers. Does anybody doesn't know what a ruggedized cover is? If there's anybody, then ruggedized cover is like having an aluminum casing, chassis around the PCB and components. And what attaches the components to the chassis above it is some kind of thermal interface material. And here you see how can we make improvements. That's our goal. We need to, in the end, we want to reduce the gradient from the thermal gradient from the chip itself, from the statics, from the FPGA, to the final heatsink, which is, I don't know, the world. And on the chip level, what we did is first we had, since mechanical engineers wanted safety, they wanted the chip to be safe, and FPGA has many balls under it. They can get hurt when they squeeze with thermal interface materials. Then they use a Berkeley's ultra soft thermal pad, which carries conduction coefficient of about 1 watt to millikelvin. And what we had to do is use putty kind of thermal interface material. We're going to talk about thermal interface materials so you're going to understand what the putty means exactly. And we got on our voyage from the network, from the chip itself, the thermal resistance down, the delta T down to actually saved 8 degrees only on the thermal pad itself. That's a lot. On the board level, we had an aluminum ruggedized cover, which means that from the chip itself, after it passes the thermal interface materials, it needs to get to the sides of the ruggedized cover, where it's shrinking by hallmarks, by wedge locks, and then cooled by let's say two, we will see that afterwards, two cold walls with raised cold plates or not. What we did is turned to a copper ruggedized cover. Of course, there's a decrease in temperature here, but it's not that. I mean, what we did here is like thinking very small, because we didn't think about problems by doing that. Of course, copper is a lot more conductive. It has 395 watt megakelvins against the aluminum, the 6061, which is about 169. So we got 5 degrees off between the chip itself and the hallmarks, but we added a lot of weight. That's one. And the second thing, we might have caused a galvanic cell, because the ruggedized cover is going to be attached to aluminum, and that could cause problems. What we did again is turned to an aluminum flow-through cover. We're going to see afterward what this means. This means that the flow flows through the aluminum itself, through the cover itself. The cover is a cold plate, and we have been able to reduce, again, from 10 degrees to 1 degree without changing the material. That's one order of magnitude improvement. That's a lot. In the system level, there was a military electronic equipment. We had ECS. The ECS controls the environmental conditions everywhere in the plane. And we had constant, first part inconsistent, damping component level delta T, CS mass per 360. You just simply had to increase the mass flow rate to, but that's not something that you're always going to. Sometimes this means you need a different thermal solution. You need to shift. But now we're talking about component level. When we're talking about component level, there is the thermal resistance term, which has in its own both the length of that heat does from one point to another, and the area that he moves through. So we can say that thermal resistance is a property which is not dependable upon size, upon length, or the area of the component. Usually, the most simplistic model we use for chips is, and what we get when we get a data sheet, is a two resistors model. It has thermal resistance from the junction where the silicon is to the base, to the PCB, and one to the upper case, which means that if we look at the PCB, such a model means that the top wall is isothermic, the wall is isothermic too. It can't have, because this is a 1D actually model, and according to JEDEC, which is the standard for electronics and components, you shouldn't use these numbers for analysis. So I don't know how many of you here are thermal engineers. Possibly some of you are thermal engineers, some of you are mechanical engineers, that design engineers that want to know a little bit more about thermal stuff. Some of you are system engineers, but even those of you who are thermal analysis engineers do not know that the recommendation is, it's not even a recommendation, it's like a mark signed written. Don't use these values for thermal analysis. These values are environmental conditions dependent, usually 25 degrees, which means that if I have an ambient temperature of 70 degrees or 71 degrees or 55 degrees on a hot day, which is very relevant, then the values are different. And but we use them anyway. Why? Because we don't have anything better. So one of the biggest, if we're not talking about forced convection, which then turbulence center, and then we have only conduction and pure conduction. Usually we solve problems like this with pure conduction. The largest error would be on the chip itself. So turning to the vendor and asking for a better model, we're going to see what better model means.